So today I'm going to discuss the concept about matrix formulation for plane trusses. So a plane truss is an assembly of straight members that are assumed to be pin connected to their ends. The degree of static indeterminacy of a 2D truss is from theory 1 is equal to number of reactions plus number of bars minus the number of equilibrium equations, which is equal to 2j. For 3D truss, then it is R plus B reactions plus bars minus 3 times J. But we are interested in the degree of kinematic indeterminacy, that is the total degree of freedom minus 3. So 3 bars and truss bars and bars in the preceding chapter differ only in the degree of freedom, for the former has 2 degrees of freedom while the latter has only 1 degree of freedom per node or joint. The plane truss shown below has 7 degrees of freedom, 0 at the pin support, 1 at the other ruler support, and 2 per node without a support. So for 4, there is no degree of freedom because this is a pin and movement along X and along Y are constrained. At 1, there's only one movement and that is horizontal. So at nodes 2, 3, 5, each node has 2 degrees of freedom, then plus 1 at node 1, then that makes it 7 degrees of freedom. Therefore, there are 7 unknowns in this truss, the 7 degrees of freedom or the 7 displacements. Another difference between a bar of a plane truss and a bar in the preceding chapter is that a truss bar can be inclined while the bars in the preceding chapter can be oriented either horizontally or vertically. So let's now proceed to the coordinate transformations. Let's consider the truss element shown below. The global displacements are the U's, while the local displacements are the deltas. So at each end of a truss member, the local displacements are denoted by delta 1 and delta 2, while at the other end, delta 3 and delta 4. While the global displacements are U1, or the X component of the displacement, and U2, the Y component of the displacement, as well as on the other end, U3 and U4. Take note that a truss member is actually loaded member. So the forces on a truss member will be along the axis of the member. There's no component of force perpendicular to the axis of the member. So therefore, there will be no P2 and P4 respectively. The elemental or member stiffness matrix is 4 by 4 because there are 2 degrees of freedom per end. So 2 at this end and another 2 at the other end. So that makes it 4 by 4 in this form. Now P1, P2, P3, P4 equals 1, 0, negative 1, 0, 0, 0, then negative 1, 0, 0, 0, 1, 0, 0, 1. And we have delta 1, delta 2, delta 3, delta 4. Take note that this is the 1, negative 1, negative 1, 1 are the elemental stiffness matrix for a bar, in which in this case delta 1 and delta 3 coincide with the axis of the bar. There is no P2 and P4, that's why in rows 2 and 4 all the elements or all the forces will be 0. or we call this uh, force coefficients 0, because there should be no P2 and P4 in these directions perpendicular to the axis of the bar. Because I already stated that a bar, a truss member is subjected to an axial load only. Elements of rows 1 and 3 are the salts of force coefficients of a bar, if you remember. So we only do not put the K here, which is AE over L. The global forces or system forces are denoted by the Fs, such as Fx and Fy, which are parallel to the global XY system. So if we have here a truss, and there is a horizontal force at 5, then that's the Fx. And the loads, vertical loads, are the Fy's. As well as the component reactions. So at 1, there is Ry or Fy. And at 4, we have X component and Y component of reactions. So they are considered F's. While the local force is the axial force of a member, which is either tension or compression. And they are denoted, the local forces are denoted by P's, such as P sub 1 and P sub 3, which are parallel to the local X prime and Y prime axis. So expressing the local displacements, deltas, in terms of the global displacements used will take the form delta matrix is equal to beta matrix times the global displacement U matrix, where beta is called the beta transformation matrix, which is necessary to coincide the local coordinate matrix or transform the local coordinate matrix into global coordinate matrix. So let's consider the figure shown in order to relate deltas with the global displacement U's, and assuming that the local coordinate system, the x prime and the y prime axis, are rotated theta degrees counterclockwise from the x-axis, or theta radians counterclockwise from the global axis, which are the x and the y axis. So this is the displacement u, and this is also the displacement delta. The vector lengths u and delta are the same. So with respect to the global coordinate system, this is u1. So that's u, this is u sub 1, and parallel to the y-axis is u sub 2. So we need to express the deltas into the u's. So the delta matrix, delta 1, for example, is the length or the projection of this global displacement along the x prime axis and along the y prime axis. So this is therefore delta 1, the blue displacement, parallel to the x prime axis and perpendicular to the x prime axis, is the delta 2. So take note that we have here a right triangle with u1 as the hypotenuse. Then we draw a line perpendicular to the x prime axis to form this right triangle, and that's delta 2. So this is the right triangle that I mentioned earlier. So this is u1, the hypotenuse of this right triangle. This right triangle has two components, namely this component here, which is u1 cosine of theta, and this component here, which is u1 sine theta. So also this angle of rotation is also theta as well as that angle theta. So therefore this is u1 cosine theta, which is equal to the length of this leg of this right triangle here. So again, imagine that this is u1, the hypotenuse of this right triangle. So the adjacent side is u1 cosine theta. The opposite side is u1 sine of theta. Likewise, in this right triangle, I hope you can clearly see it. We have theta, the hypotenuse is u2, then this is opposite. Therefore, this opposite side is u sub 2 sine of theta, that one. So, which is equal to this length here. That's u2 sine theta. And the adjacent side, which is this, is u2 cosine theta. But before that, we observe that delta 1 is equal to u1 cosine theta plus u2 sine theta. So, the length of this component of this right triangle is u2 cosine theta, this one, which is equal to this length here. So that is u2 cosine theta. And the opposite side of this right triangle is hypotenuse u2 times the sine of theta. This is u2 sine theta, which we already established. Then, as I said, this component of this right triangle is u1 sine theta, which is now this one. So u1 sine theta. So delta 2, on the other hand, is u2 cosine theta minus u1 sine of theta. So delta 1, u1 cosine theta plus u2 sine theta. Delta 2 is u2 cosine theta minus u1 sine theta. So this is at one end of a truss member. Similarly, on the other end of the truss member, we simply replace the subscripts 3 and 4. So delta 3 therefore is u3 cosine theta plus u4 sine theta, and delta 4 is u4 cosine theta minus u3 sine theta. Writing equation 4.2 in matrix form, then we have the delta matrix, which is a column matrix, delta 1, delta 2, delta 3, delta 4, then equals the beta matrix would be cosine theta, sine theta, then 0, 0, 4 by 4, then row 2 would be negative sine theta, cosine theta, 0, 0. Row 3 would be 0, 0, then cosine theta, sine theta, then row 4 would be 0, 0, negative sine theta, cosine theta. Then times the global displacement matrix, which is U1, U2, U3, U4. So again, this is now the result. Delta 1, delta 2, delta 3, delta 4 equals the beta matrix, which is cosine theta, sine theta, 0, 0, then negative sine theta here, cosine theta, 0, 0, then 0, 0, cosine theta, sine theta, then 0, 0, negative sine theta, cosine theta, then we have u1, u2, u3, u4. So you can verify these equations to match with this matrix equation. And of course, the column numbering. Also by vector lengths, because delta equals u, the magnitude delta is square root of delta 1 square, delta 1 square plus delta 2 square, this right triangle here. So it is equal to, by Pythagoras, square root of delta 1 square plus delta 2 square. And this is also equal to u1 square plus u2 square. So it's the same. So therefore, square both sides. So we have delta square equals u square, and delta is delta 1 square plus delta 2 square, and it is equal to u1 square plus u2 square. So writing delta 1 square plus delta 2 square in matrix form, horizontal row matrix, then column matrix, and u1, u2 also in matrix form, u1, u2 horizontal, then u1, u2 column matrix, vertical. Take note that they're the same. And considering the column matrix as delta, this delta 1, delta 2 as delta, and this u1, u2 as u. Therefore, this row matrix would be the transform or the transpose rather of the delta matrix. So this is delta transpose times delta equals u transpose times u. So call that equation 4.4. Then since delta is equal to beta times u from equation 4.2, if we solve for the global displacements, so it is equal to the inverse of beta times the delta matrix. So call that equation 4.5. Then since from this equation, if we obtain the transpose of delta, then remember from property of matrix multiplication, when you have A times B quantity transpose, then it should be B transpose times A transpose. So you have to reverse the order of the product of matrices on the right side. So therefore, delta transpose is equal to U transpose times beta transpose. So substitute these equations 4.5 and 4.6 into equation 4.4, then we get uh, delta transpose, which is U transpose beta transpose times delta equals U transpose times inverse of beta, this U here, times delta. So canceling out U transpose and delta, and the result gives us this wonderful relations that beta transpose is equal to the inverse of beta. If you can remember, this is the property of an orthogonal matrix, which is important for rotational relation or orthogonal rotation of an orthogonal system. So again, the inverse of beta is simply the transpose of beta. That's a result from equation 4.7. So we now proceed to the derivation of the global stiffness matrix. So though the local coordinate axis of a bar coincide with the global coordinate system, especially one axis there, we now transform its elemental stiffness to a common global coordinate axis in order to generate the global stiffness matrix. So we transform the local coordinate system into the global coordinate system in order to derive this global stiffness matrix. So equation 4.2 can also be used in transforming local forces, the P's, into the global forces, which are denoted by F's. So that is P matrix, local force matrix P is equal to beta times the F matrix. So take note of the similarity. Then for the elemental stiffness matrix, P is equal to K times delta, and delta is equal to beta matrix times U. So bet this P here from equation 4.8 is actually this one, and it is equal to beta matrix times the force matrix. So that substituting this equation 4.2 into equation 4.10, then delta, which is beta times U, so we have K matrix for individual bar times beta matrix times U equals beta matrix times F. So if we solve for F, then it is the inverse of this beta times this value here. So F matrix, global stiffness matrix, F is equal to inverse of beta times this product of matrices, the K times the beta times the global displacement matrix. So this is now the formula for F. So take note of this highlighted value because F is a certain matrix times the global displacement matrix, then we can say that this is the stiffness of the global system. So we can denote this by capital K. And take note because beta is simply the transpose, the inverse of beta is simply the transpose of beta, and we can use beta transpose instead of inverse of beta. So again, the local P matrix is equal to the stiffness matrix K times the local displacements. And since this local displacements is transformed into or related into the global displacements in this form beta times the global displacements, then the force displacement relationship for the global coordinate system, F is in this form capital K for the global stiffness matrix times the global displacement. So, which is beta inverse times K times beta times U. So, F therefore is equal to capital K times U. So, replacing beta matrix by or inverse of beta by beta transpose. So K is also beta transpose times K times the beta matrix. So the global forces is written in the form as capital K global times U global. So this equation 4.13 is the key in transforming the elemental stiffness matrix small k with respect to the local coordinate system to the elemental stiffness capital K with respect to the global coordinate system. So that is F is equal to, for the entire structure, F is equal, global is equal to K, capital K global times U global. So expanding equation 4.13 and denoting C for cosine theta and S for sine theta to make the stiffness, to make the beta transformation matrix compact. So K global is equal to EA over L for the coefficient for K here. Then this is the beta transpose. This is the stiffness matrix K times 1, 0, negative 1, 0, then rho 2 is 0 for P, for delta. Then negative 1, 0, 1, 0, rho 4 is 0, which we already derived in the preceding slides, times the beta matrix again, which is CS00, then negative SC00, 00, CS, 00, negative SC. So you just take note of this. This was, I think, equation 4.3. Equation 4.3. Then this is the inverse or the transpose of this matrix here. So CS00 in column, negative SC, then 00, then 00 CS, 00 CS, then 00 negative SC. So if we simplify this by performing the product, beta transpose times the K matrix times the beta matrix. The result would be easy to remember. So K global equals EA over L times quantity C square, CS, CS S square. Then the whole of this would be the negative of these elements. Negative C square, negative CS, negative of CS, negative of S square. Then this is copied in this position here. They're the same. And the 4 by 4 matrix in this portion is also copied in this portion. So it's very easy to remember. It's just EA over L. All you have to do is memorize these first 2 by 2 matrix here. And take note that on this side here, it will be the negatives of these elements here. Then, by symmetry, because the global stiffness matrix is symmetric, so that's why it's the same here. And this is also the same here. So I hope you can easily memorize that. So for the member force, P is K delta, or it is equal to the stiffness matrix K times beta matrix times U. So substituting the value of K, which is EA over L times this matrix here. Then the beta matrix, which is this. Then times the global displacement matrix. So that's the member force. If we simplify this further by getting the product of these 4 by 4 matrices, then we have, to be specific, P1, P2, P3, P4 equals E over L, and you have CS negative, the negative of these first two row elements here. Then remember that P2 under or along with the level of P2, that row would be all zeros because there's no P2. Then P3 will be the negative of the first row. So negative of C, negative of S, negative of negative C, negative of negative S. That's it. Then row 4 will also be zeros. So that's the member force. And the numbering is 1, 2, 3, 4 if member 1 is numbered from 1 to 2. So 1 to 2. So that's why it's 1, 2, 3, 4. Likewise, if we have member 2, which is numbered 2 to 3, then this is same. And you have U1, U2, you have U3, U4, U5, U6 here. And that's the member force for member 2. So as long as member 2 is numbered 2 to 3. So if you double that, that's 4 and 6. That's why you also have 4 and 6 here. Then for member 3, if it is numbered 1 to 3, then it is P1, P2, P5, P6. Then we have EA over L, same beta matrix. Then we have here, by the way, this is the product of this matrix and that matrix. And you have here U1, U2, U5, U6. If member 2 is numbered 1 to 3. So let's refer to our truss in the preceding slide. So if this is why this is denoted member 1 because it is bounded from 1 to 2. And that's member 1. Member 2 is bounded from 2 to 3. And member 3 is bounded 1 to 3. And so on and so forth. So that's for matrix formulation. So remember the global stiffness matrix. It's easy to remember, as well as the member force calculation. You look at the matrix for member forces. It's also easy to remember.